Dear students, friends and learners, I am Shashank Shrivastava from School of Engineering and Technology, IGNOU. So in this session, we will see about different process of stainless steel heat treatment process, and further we will discuss about cast iron and other things. Further, we discuss the process of hardening and tempering. And these processes are meant only for the martensitic type of stainless steel. This you have to note down. The steel, this kind of steel is heated to a temperature of 950 to 1050 degrees centigrade, and then it is quenched in air or oil, resulting in formation of hard martensite. And the quenched steel is then tempered between 100 degree and 700 degrees centigrade depending upon the required hardness. So this temperature you can vary depending upon the hardness you require in your specimen. Further special treatments are there for stabilized grade of austenitic steel. So this special treatment, in this special treatment, steel is heated to 870 to 900 degrees centigrade, and there it is held for almost 2 to 4 hours. And then further it is quenched in either air, oil or water, and this quenching will cause the precipitation of titanium or columbium carbide. So these two carbides will actually prevent the precipitation of chromium carbide, which is a dangerous thing during the service life. Further, now we discuss about the post-weld treatment. We earlier saw how weldability is affected in many cases, so we need post-weld treatment also. So welding, we know this process actually induces undesirable residual stresses, and thus the corrosion resistance is reduced. And weld decay, if you have read about the manufacturing science and the welding process, so you must be knowing about one defect that is called the weld decay, and it's a common welding defect in stainless steel, and this is caused by what? Precipitation of carbide of chromium. Again chromium carbide is coming, and this is formed in the weld region and the heat affected zone. HAZ means heat affected zone. The result of the precipitation is great susceptibility to intercrystalline cracking. So due to this chromium carbide, there can be intercrystalline cracking, and there is reduction in the corrosion resistance. Stress relieving annealing or solution annealing, the three processes which we discussed earlier, these are the treatments recommended for weldments before putting them to use. So we need these kinds of process before the welding can be said to be accurate or fine. So after discussing the heat treatment of the SS, we now discuss the heat treatment of the tool steel. So again the same processes are there, like the normalizing and the annealing, and they are very necessary, especially in the case of the forged type of tools. Forging is a process which we study in the manufacturing science, so in that case we need these processes. Normalizing here is carried out to remove undesirable residual stresses, coarse grains and non-uniform structure. So mostly you see all these processes are meant for removing the residual stresses, and also sometimes this coarse grain structure. Why? Because this coarse grain will not form a compact structure, and its strength will be lower. That's why we want to remove coarse grains also, and we want a homogeneous structure. The tools are machined to exact dimensions after normalizing, and this causes strain hardening. So after the normalizing process is over, what happens that the tools are machined, because they have to be made to certain exact dimensions, and due to this machining process another defect comes in, a kind of defect, that is strain hardening, and it can be detrimental for certain things. The intermediate annealing from just below lower critical temperature is applied upon the tool to remove this strain hardening. So now we have a solution to remove this strain hardening, which we discussed just now. What will we do? We will do intermediate annealing from just below lower critical temperature, that means around 723 degrees centigrade. The tool steels have generally lower thermal conductivity. That means the heat loss will not take place at a good rate, and if the tool is heated at a faster rate, then what will happen, that some portion will be hotter and some will remain cool, because the thermal conductivity is less, and it will lead to distortion and cracking may occur. To avoid such things, cracking and distortion, the tool before any treatment will be preheated slowly to temperature around 600 to 800 degrees centigrade. This preheating is very important because we have to prevent the cracks and distortion. The tool is held at the preheat temperature. This is the process for this. It is held at the preheat temperature sufficiently long, meaning we have to give certain time to allow whole body to come up to a uniform temperature. That's why I told you earlier that one portion is at a certain temperature, the other one is at a cooler temperature. So that difference cannot be allowed. We need a uniform temperature throughout the whole body, and for this process of preheating is done. And in this way we heat it to the required temperature and the treatment is over. Now we discuss about the process of tempering and stabilization. So this one is done, these two processes, tempering and stabilization, to minimize the existence of untempered martensite, retained austenite and carbide in the structure. So all these things actually pose difficulties or problems, so that's why we want to minimize these things. And reason again is same, that residual things are there and they do not permit to establish correct austenizing temperature. Tempering, besides removing these structural deficiencies, also help induce secondary hardness. So tempering is a very good process. It helps to remove the structural deficiencies and at the same time it helps to induce secondary hardness. After tempering, initially the treatment is repeated 2 or 3 times in multi-tempering practice. So we can go for multi-tempering also if we want a certain grade of steel or tool steel or whatever we want. And further cool the tempered steel to sub-zero temperature by placing it in solid carbon dioxide, which is around -75 degrees centigrade, or dropping it in liquid nitrogen. So these two things are also there, solid carbon dioxide or liquid nitrogen. So in that way we can get our products, and this will help to stabilize the steel. So after discussing about the stainless steel and the heat treatment process of the stainless steel and high carbon steel, we now come to the cast iron, which is also very important. So its name comes from the casting process because it is very easy to cast this type of materials. That's why it is called cast iron, and it is easy to cast with intricate and good mechanical properties. So it gives us good mechanical properties, this cast iron. There is a eutectic point actually, like you have read in the previous sessions, which is 4.3% of carbon, and it has a solidification temperature of 1135 degrees centigrade. So alloys within the carbon range of 2.3 to 4.2% actually, they come under this category of cast iron, and they are referred to as hypoeutectic irons and come under this category. They are referred to hypereutectic if it is more than 0.8% of carbon. Although the melting points of cast irons are much higher than several non-ferrous alloys, yet they are within the reach of simple melting furnaces, several of which are commercially available. So we can see that melting point of cast iron is much higher than non-ferrous alloys, but still we are using it because there are simple melting furnaces for this cast iron. That's why it is very commercially viable for us. And what are the properties of cast iron? It is a very cheap material, so it can be used extensively, and it is a lower melting point around 1200 degrees centigrade as compared to steel, that is 1380 to 1500 degrees centigrade. So why lower melting is needed? Because then it can go into the liquid form easily and can be casted into different shapes. So the point coming in, that is good casting properties, and that means high fluidity and low shrinkage, sound casting, ease of production and large number. And it is good in compression. The compressive strength of cast iron is very good, but ductility is not that much, but still ductile CI is also available, and it is machinable in most cases. Then it has remarkable abrasion resistance, that means its hardness is also very good, and it has excellent damping characteristics, So this damping characteristics actually makes it very well known in different industries, because we can use it in the foundation and the housing, where we want the damping process to take place and the vibrations to die down, because it helps to isolate the vibrations. Suppose even if there is an earthquake, then our housing structure has such type of material which can absorb that, then it will be very good. So cast iron is that type of material, and alloy cast iron is good against the corrosion also. So constituents of cast iron: it is carbon content of more than 2%, and silicon is around 0.5 to 3%, and the silicon actually controls the form of carbon in cast iron. Sulfur content actually varies from 0.06 to 0.12, and sulfur actually is present in the form of ferric sulfide, that is FeS, which tends to melt at comparatively low temperature, causing hot sharpness. So when we are heating it, this phenomena can occur, that hot shortness, meaning that embrittlement can occur. So sulfur is not a very good thing for cast iron also. And manganese actually inhibits the formation of this ferric sulfide FeS. So if we have sulfur, then we can add manganese, because it will help to prevent the formation of iron sulfide, which is detrimental to cast iron. Phosphorus, in case of cast iron, it increases fluidity, so it is helpful for pouring process. So phosphorus is not that bad for CI, and phosphorus but again has to be restricted between 0.1 to 0.3%, because it reduces the toughness. So toughness of CI will be reduced if phosphorus goes beyond a certain limit, and it is generally present in the form of FeP. The chemical formula is FeP, that is iron phosphate, we can say. Manganese in cast iron is in the range of 0.1 to 1%, and this helps to improve upon the hot shortness by taking care of the sulfur. So again the manganese is helpful here, because it reduces FeS. Now the classification of the cast iron: there are various categories: white cast iron, grey cast iron, nodular cast iron, and the mechanite cast iron. So these are the most basic 4 types. Now we discuss the first one, that is the white cast iron. So it contains carbon in the form of cementite. Like we discussed earlier in the previous sessions, cementite was there, which is given by the chemical formula Fe3C. So here again it comes in, because the percentage carbon is in that range beyond 0.8%, and it also consists of perlite, cementite, and ladeuberite. So it has both things, it has cementite also and it has perlite also. So that is the carbon range in case of white cast iron, and it has a high hardness and wear resistance also, but is difficult to machine, but it still can be ground. Grinding is a process in the manufacturing, like there are grinding wheels, so it can be ground. Hardness of white CI varies between 300 to 500 Brinell hardness number, and the ultimate tensile strength, that is UTS, is between 140 to 180 megapascal. Normally sand casting is used to produce such parts as pump liners, mill liners, grinding balls, etc. So these are some of the applications of this type of cast iron, which is white cast iron. After discussing the white cast iron, we now go on to grey cast iron, that is the cast iron which is containing carbon in the form of graphite flakes. So there are flakes. Flakes are like some small particles, you can say. They have a certain shape, and these are of graphite, and these are dispersed in the matrix of ferrite or perlite. Thus they are called the grey cast iron. So this flakes of graphite are in a mixture with ferrite or perlite, and this name is derived from the fact that a fracture surface appears grey. So in the case of this iron, if there is a fracture surface, then it will be of grey color. Grey cast iron differs in percentage of silicon from white cast iron, while carbon percentage is almost the same. When discussing about this grey cast iron, we will discuss about the making process also, how it is made. So the liquid alloy of suitable composition is cooled slowly in sand mold. There's a sand mold, and liquid is poured inside it, and then this decomposes Fe3C, that is the cementite, into Fe and C. So both separate out, and the separated C is precipitated in the form of graphite flakes, which we discussed earlier. So this graphite flakes are coming from Fe3C only when both are separated. Addition of silicon, aluminium or nickel will accelerate this graphitization. So graphite flakes vary in length from 0.01 to 1 millimeter. So these are the dimensions of these graphite flakes. So the graphite flakes that are present in this grey cast iron, actually they provide an easy passage to cracks, thus not allowing softer microstructure to deform plastically. So if we need to deform this grey cast iron plastically, then it becomes difficult if these graphite flakes are present, because they do not allow such process to happen. So certain process will be hindered then. Larger flakes reduce strength and ductility also. So these flakes are not good as such, because they are not allowing plasticity also, and they are not allowing good strength and ductility as well. Now the properties of this grey cast iron, it is basically brittle, because you saw the reason just before this, that there are flakes which are not allowing plasticity, so it will be brittle, with hardness varying between 140 to 320 Brinell hardness number, and ultimate tensile strength from 150 to 400 megapascal. But it has excellent fluidity and high damping capacity and machinability. Again, so it can be used in structures because high damping capacity is there. And if grey CI is repeatedly heated in service to about 400 degrees centigrade, it suffers from permanent expansion called growth. So if that temperature is reaching at different intervals while in service, then it undergoes the process of expansion, and this expansion is permanent. Ductility and strength due to this growth will then be less. When locally heated to about 50 degrees centigrade several times, this material develops what are called fire cracks, resulting into failure. So suppose this grey cast iron specimen is there, and if at a certain point we are heating this specimen up to 550 degrees centigrade, and we are doing this repeatedly, this process, then what will happen? Cracks will develop and fire will be there. So these are known as fire cracks, and ultimately the specimen will fail. Now we discuss the mechanite iron, which is the third variety of the cast iron. We have discussed earlier the white and the grey one. So mechanite iron, high strength grey cast iron, is obtained by addition of strong inoculating agent like calcium silicate to liquid metal before casting process. So this is the process for this one, and ultimate tensile strength for this one is in the range of 250 to 400 megapascal. And this cast iron is known as mechanite, and it can be toughened also by oil quenching treatment, and after toughness the ultimate tensile strength goes up to 520 megapascal. Further, a very important type of cast iron we have come to, which is nodular cast iron. If the graphite present in the cast iron is present in the form of nodules or spheroids. So earlier what we studied, in grey cast iron we studied about the flakes. Now we do not have graphite flakes, we have nodules or spheroids, and they are in the matrix of perlite. So this cast iron has marked ductility. So that's the difference you can see. Instead of flakes, if you have nodules, then ductility comes in, otherwise it is not there. So this ductility gives us the advantage of different kinds, and this process gives us a better nodular cast iron, which can be employed in different places. It is basically a grey cast iron with composition as such. So this one is also a kind of grey cast iron only, but here spheroids are present instead of flakes. So carbon percentage is as such 3.2 to 4.1%, and silicon is 1 to 2.8%, and we have sulfur and phosphorus in very low percentage, 0.03 to 0.1% respectively, and we have also nickel and magnesium, which are added as alloying elements to make its properties better. What are the applications for this one? Nodular cast iron. It is used in various places like the crankshafts, metal working rolls, punch and sheet metal dies and gears made of this thing, because it has got toughness also. It is not simply brittle as in case of grey cast iron. There are lack of defects like growth and fire cracks, which we saw in grey cast iron, so it makes it suitable for making furnace doors, sand casting and steam plants also. And due to the presence of nickel, it has good corrosion resistance, hence it is useful for chemical plants, petroleum industry and marine applications. After discussing the nodular type, we come to the malleable type of cast iron. What is the process for making it? So here the white cast iron, which was the second type, and containing 2 to 3% carbon, 0.9 to 1.65% of silicon, sulfur and phosphorus are lesser than 0.18%, little manganese and bismuth, and boron less than 0.01%. Then this one can be heat treated for 50 hours to several days to produce temper carbon in the matrix of ferrite or perlite, thus imparting malleability to Ci. So this is the process for making the malleable cast iron, and these can have as high as 100 megapascal of ultimate tensile strength and 14% elongation also. So this one can be made in the form of sheets, malleable cast iron, and it can be used in various purposes. So the applications of malleable cast iron, it has properties like greater strength, ductility, machinability, wear resistance, and also convenience of casting in various shapes. So the applications are like in automotive parts, in crank and camshafts, steering brackets, shaft brackets, brake carriers, etc. And also in electrical industry, in the manufacturing of switch gear parts, fittings for high and low voltage transmission and distribution system for railway electrification. So this type of malleable cast iron is also very useful. In this session, we have learnt about the different kinds of stainless steels and the cast irons, various types of cast irons we have studied, and the various processes of heat treatments of stainless steel and cast iron as well. Thank you very much.